Morning everyone. Hope you're enjoying your snow day. I thought I'd just go through carboxylic acids today, both the introduction that I did for one class on Monday and also the next section. So we're doing carboxylic acids, and you're familiar enough with that functional group, I'm sure. Contains the CO double bond carbonyl group, but remember, a carbonyl group is not a functional group, it appears in just too many different molecules. And then the OH, the hydroxy, together they make a carboxylic acid. Of course, the most important feature of carboxylic acids is that they're acids. So if I take an acid like ethanoic acid, it will react with, well, acids react with bases. We did this before in acids and bases, and of course we've been doing reactions of acids and bases since year 9. We could also take a different acid and react it with a metal, say. And we could take that acid and react it with carbonate. Okay, so you should be able to work out the products of those reactions. That would be a fairly standard A-level question. They'll probably add some balancing in there as well. Just pause the video now and have a go at doing those. Okay, so with ethanoic acid, of course, the H from the acid group is lost or dissociated, and the sodium comes in. So we can either write the product as OO minus Na plus, showing the ethanoate ion there, or we could show it just as like a single compound, like the formula would be on the side of a bottle of solid. But what we can't do is show any kind of covalent bond between the oxygen and the Na. Okay, don't do that. Of course, the other product here is water. With magnesium, we get salt and hydrogen. Metal and acid make salt and hydrogen, the MASH equation. Of course, magnesium is in group 2, so it forms a 2 plus ion. So I'll need 2 of those to balance the charge on the ion. And some balancing, thanks. And then with sodium carbonate, we get the salt, COONA again, and then carbon dioxide and water. Moving on, let's look at the naming of carboxylic acids. So I'm sure you're familiar with the standard meth, eth, prop, bute for 1, 2, 3, 4 carbons in the molecule. So we go methanoic, ethanoic, propanoic, butanoic acid. If we have any kind of substitution, let's say put a methyl in there. Let's make it another one. There we go. So we've got 4 carbons as butanoic acid, and then we've got a methyl group sitting on the butanoic acid. So we just have to number it to identify the position. Well, by default, the acid group will always be carbon 1. The acid has to be at the end of a molecule, but it also takes priority as the most important functional group. So carbon 1, carbon 2, carbon 3, so it's 3 methyl butanoic acid. So these other three molecules here, I don't know how well you can see the overhead. I'll put it in the I'll put it in with the downloads on your homework on Satchel. Just simple like that. The ring, I know we haven't gone into a lot of detail about this ring of 6 carbons called the benzene ring, sometimes called a phenyl group when it's attached to something else. So either a phenyl group or a benzene ring. We'll go into naming those in the next topic. Just have a go at naming those 3 molecules there. So 3 chlorines would just be trichloroethanoic acid. If you were going to put numbers on, well, that's carbon 1, that would be carbon 2, so it would have to be 2,2,2 trichloroethanoic acid. The chlorines can't be anywhere else, so we don't need the 2,2,2. If you put it in your answer in an AQA exam, you won't get it wrong. If you write 1,1,1 trichloroethanoic acid, you get that wrong. So again, COOH takes priority, and that's carbon 1, so it's going to be propanoic acid with a hydroxy group rather than an alcohol. So 3-hydroxy propanoic acid. And then this molecule has various names. The most systematic name, I think, would just be to say we've got a phenyl ring and methanoic acid, so phenyl methanoic acid. But that's a rather long and clumsy name for a molecule which is pretty common and used quite a lot in industry, so it tends to just be called benzoic acid. We mentioned, of course, that acids are acidic, and so they dissociate. Remember that a weak acid weakly dissociates into ions. So 99% of ethanoic acid stays as ethanoic acid molecules, and only about 1% of it dissociates at any one time. So we've got a weak acid. All the organic acids are weak acids. So we can write the equation for the dissociation constant, sorry, not the equation, the expression for the dissociation constant, Ka, for an acid. And we can rearrange that to work out the pH of an acid if we look up its pKa value, which is 4.76. So could you work out the pH of 0.15 mole per dm cubed ethanoic acid for me? Pause the video now and have a go at that on your own. So if we rearrange that equation and make some assumptions, we can get ourselves down to the weak acid formula, which is H plus is the square root of Ka times the concentration of the acid. We'll need the Ka first, so Ka is 10 to the minus pKa. So 10 to the minus 4.76 is 1.74 times 10 to the minus 5 times the concentration of the acid. Gives us a concentration of H plus, which I didn't work out in advance. Times 0.15 and square root it. This calculator doesn't like it if I do that. Why do calculators stop not allowing you just to square root the button, the number in the calculator? Right, let's do that again. It's a live show, folks. I mean, it's obviously not a live show. Square root. Hooray, it works on this calculator because Casio. 1.62 times 10 to the minus 3, and if I hit the log button and minus the answer, 2.79 to 2 decimal places, of course. Okay, the next thing I'd like to talk about is making esters. So this is a topic that you've probably had mentioned before, maybe in the alcohol section, maybe even in your GCSE. If we take an acid and react it with an alcohol, then throw in a dehydrating agent. The dehydrating agent we use is concentrated H2SO4. The dehydrating agent absorbs water. So if I remove water from those two molecules, take the H off the acid and the OH off the alcohol, then we're left with two bits which can then stick together with a new bond and make this molecule. And that's an ester. So the ester is a functional group which looks a little bit like the carboxylic acid group, except we have a carbon attached to the oxygen here instead. So we've got carbon, oxygen, oxygen, carbon. So that's and then whatever's attached to that carbon there. That's our ester functional group there. And obviously there'll be more ones coming out of there. You get it. To name the esters, so there are two parts to the ester. There's the part that came from the alcohol, the ethyl group, and then there's the part that came from the acid, in this case the ethanoic acid group, but then we swap them round. So the name of this ester is ethyl ethanoate, and then that's the name ending for the ester group, the O8 group. So ethyl ethanoate is the name there. So there's some esters on the board there. Pause the video now to have a go at working out the names and the formulae of those esters there. Good sound. Right, so number one, so I've got the acid group there, the methanoic acid, and then I've got the alcohol there. Of course, we have to attach from the end where the OH is, so that's the CH2 end, so it attaches that way. So that's an ethyl group there. One carbon is meth, so it's ethyl methanoate. Question 2, I've got my acid group there, and then just a one carbon alcohol on the end. So now I've got a methyl group here, so methyl and then a 2-carbon group here, ethanoate. So you can see how naming esters could get confusing. You get these the wrong way around. You have to know what you're doing. For the third one, the acid is ethanoic acid again, the 2-carbon acid. And the alcohol is now 3 carbons. So that will be a propyl group. And then the 2 carbons gives us ethanoate again. This one looks very similar, except the alcohol now is joined from the middle carbon. So we've got a CH on the middle and 2 CH3s either side. Well, how do we name that? Well, we go for the longest chain that's attached to the oxygen, which is actually just an ethyl group. And then we have a methyl group attached to the ethyl group. So it must be methyl, ethyl, and then the 2-carbon acid part, ethanoate. And lastly, the benzoic acid molecule has reacted with butanol, but again, I've got a methyl group kind of hanging off there, so CH, CH2, CH3. So I've got a propyl group and a methyl group, but the methyl group could be there or it could be sitting on the middle carbon there, so we have to distinguish, and again we distinguish with numbers. So 1 methyl propyl is the group there, and then if we were naming that molecule, the original molecule was benzoic acid, then that would just be benzoate. Okay? And just before we finish today, what about this interesting molecule here? It's an acid, yeah, carboxylic acid, but it's also an alcohol. So it's in the unique position in being a reaction that if I add conc H2SO4 to, could react with itself. So the acid end of the molecule can react with the alcohol end of the molecule. Pause the video and have a go at drawing the molecule that we make. So I'm going to have to bend it round a bit. Let's just count the number of groups I'm going to have it in it. I'm going to have the oxygen, 1, 2, 3, 4 carbons, and then the 5th carbon in the acid group. So I've got 6 things, and it's going to be a ring. So there's my ester group. So that's the carboxylic acid end, and then that's going to attach to the alcohol end, and then we've got CH2, 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 and then we're back to the acid. It's quite neat as a skeletal formula. So it's a cyclic ester. Fortunately, we do not have to learn how to name cyclic esters. So if you're interested, they're called lactones.